said some interesting things about how the balance must, what the balance must look like for common mode to occur. Now, the other technique to understand what common mode, where common mode comes from and what it is to see it as a transmission line. So the fundamental question is, when does a line become a transmission line? And the answer is, if you're in the PLC business, then there are two bands. The one band is the so-called generic band, sorry. And the other one is the so-called broadband. Am I running out of time? 2 minutes, okay. So, suffice to say that then at some stage the line becomes a transmission line, but for the Senelec bands, you can almost always use lumped circuit analysis, because you're talking about typically 100 meters before the line becomes a transmission line. But if you're talking about broadband in the megahertz, 30 megahertz range, then it's almost always a transmission line. So this is what a multi-conductor transmission line, a lossy circuit, looks like. This is quite complicated, and we tried to model this. We are not 100% there yet. This is part of the project, and we're using Sugiura, how do you pronounce that in Japanese? Sugiura and Mr. Thomas. We were using their model, and we're seeking a solution to the so-called lossless multi-conductor transmission line equations, which is called the telegraphist equation. The solution is actually quite difficult, but we are getting pictures that looks like the measurements that we've taken. Although these pictures are not exactly at the right frequencies. Reason is, transmission lines are lossy systems, and their inductance, capacitance, resistance, and conductance are actually frequency dependent. And that makes it very difficult to predict exactly what the common mode is going to look like. Okay, so in conclusion, why are we interested in common mode? We are interested in common mode. There's some important reasons that I said at the beginning. If we want MIMO or even SIMO, which is the single input multiple output conversion, you have to have unbalance in the system, which is almost always there in a real life electrical system. If we want to model common mode, in the Senelec band, we can use lumped circuit theory. In the broadband, we can use multiple conductor transmission lines. And in the end, multiple or multi-conductor transmission lines are difficult to model because their parameters are all functions of frequency. Thank you.
Thank you. Questions?
Okay. I think everybody can hear me. Thank you. Very interesting conclusion. My question was, if just for argument's sake, during the transmission line, during the power line, there's more than one load, or basically you have several devices talking to each other.
Yes.
And then the distance between some pair of devices will be shorter.
Yes.
For example, like 10 meters, some
yes.
would be like over 100 meters.
Yes.
Then in this case, is this theoretical analysis still viable?
Yes, it's still viable, definitely. And what you will see is the moment you look at the real configuration like that, you will have lots of unbalance. In fact, it's probably very difficult to predict, if you have a real network, to predict things like input impedance. It will look like the graphs, and MIMO is probably the only answer to getting some channel capacity over the whole frequency range.
Perhaps one remark, Arnold, you looked at this from a MIMO point of view, but people who hate the noise, the interference created by power line also is there any possibility to combat interference by addressing the unbalance that you foresee?
Actually, we are trying to understand the unbalance and the common mode, but I think the truth of the matter is that we will always have the interference. As long as we have an unbalanced system, which a real power system is, we will have electromagnetic compatibility problems or interference.
Okay. More questions? Okay, thanks again. Okay. Our next talk is about the effect of the light sources on the transmission lines or network. And the speaker is
Thank you.
please.
Okay, my apologies first. I will look like a robot now. I woke up this morning with a terrible neck headache, or what do you call it, neck pain. And probably my mother-in-law had me in her dreams last night. Okay, today we have some light sources here, and we will speak about them and their effect on the power line communication channel. Let me use this one. We will talk about the channel itself, then we will show some setup and proceed to the measurements. We'll show some results and we'll conclude. I will keep talking until you stop me. The power line channel is a challenging and a harsh channel because of the heavy load and noise impairments. And those light sources, they inject conductive noise into the power line system itself. And we do these measurements to show the results of the detected harmonics from different lamps when connected to the PLC channel. We took in consideration Cyrillic band, which is probably 3 to 148.5 kilohertz. And we also took into consideration the broadband channel up to 30 megahertz. So far we have investigated the compact fluorescent lamps, LED or light emitting direct lamps, plasma lamps, fluorescent tubes or lamps, metal halide lamps, mercury vapor lamps, high pressure sodium lamps. Some of you never heard of these names probably. The first two, and this one, the fluorescent, we use them as an indoor light sources, and they are low energy ones. The metal halide lamp, mercury lamps, and high pressure, they are high energy outdoor sources or light sources. This is like just some pictures to show you the spiral. This is a mushroom one, this is semi-spiral, this is spiral, and this is standard. These are the LEDs, some of LED examples. These are some of plasma. I'm sure those who visited the red light district in Amsterdam will recognize this picture. No? They don't know? This is the types of fluorescent tubes and metal halide lamps and so on. For narrowband and broadband, the CFL is supplied, CFL or other, I'm just giving an example here. CFL or other light sources are supplied with 220 volts through a transformer and a LISN. LISN, this stands for Line Impedance Stabilization Network. It's a device that allows the 50 Hertz to 220 to go through or to pass through and stops all the communication signals. And here you use a transformer to start the LISN because the LISN causes an earth leakage current to flow, which trips the supply. And floating the LISN itself rectifies this fault condition. So these measurements were made in the time domain and discrete Fourier transform to obtain results in frequency domain and sometimes in frequency itself. We use Tektronix, oscilloscope, Tektronix, current probe, and we use Rodian Schwartz spectrum analyzers. I think two of them. Arnold De Beer will This is just to show you this. This is the listen itself. This is the current probe, and this is the spectrum analyzer. And this is, as they say, one picture worth 1,000 words. So this one is how the connection is made from the 220 through the transformer to the listen, and here to the CFL lamp through a current probe to an oscilloscope or a spectrum analyzer, and then to a computer to process the image itself. In this case, okay, this one is used only for CFL, LED, and fluorescent tubes. No, sorry, CFL and LED and plasma. This one is used for those who use magnetic ballasts. We, for metal halide lamp, high pressure sodium, and mercury vapor, we use electromagnetic ballasts. And we use an igniter to start the lamp itself. And here, the electronic, also for all the outdoor sources, light sources, plus the fluorescent tube, they use electronic ballasts. Of course, here is in the differential mode, and because the common mode is, I think, is negligible, and this is one of the standards. Talk about this. I can't remember the standard exactly or the regulation that talks about the common mode and the differential mode. Noise generation in CFLs. There is a common structure of the CFL drivers. The CFL driver itself, it consists of active rectifiers, power converters, and filters inside the CFL itself. And this is how it looks, the rectifier and the converter type. And there were 4 types of CFLs tested. And we also did some extra analysis. When we turned all those 4 together, turned them on to show the harmonics. And here we show brand A, brand B, brand C, and brand E, which are here. And here the brands, all the brands together. And this is the voltage. We can see that when we turn them all together, the channel is mostly affected. This is in current. And here, comparison of the harmonics of all lamps combined with the maximum allowable PLC signal strength in Senelic band. So this is only from 3 kHz to 150 kHz. As we see, we are still safe, we are under the maximum allowed signal. In this case, this is for the broadband, and these are the EMC levels, which also, we are also still okay with this. The LEDs, there are 2 types of LEDs, or 2 classes, active and passive. And this is just the structure of the LED itself. They either use RC divider and rectifier, or they use a rectifier and converter. And this is how the signal that we get when we connect one LED, which is less than 1 watt of output. And this is the 2 watts LED, 4 watts, and this is one LED that has 3 LEDs inside, or one lamp that has 3 LEDs inside. It's the mostly affected here, the power line channel we see. And from 3 kHz to 150 kHz, we see the LEDs are friendly with its coordinate. But from 150 kHz to 30 MHz, they compete with the EMC signal, maximum allowed signal, or sometimes they exceed it here. So the LEDs are not really, they are good, but not the best probably, or the best, we will see. Okay, the plasma is one of the states of matters, like liquid or solid. And the plasma is used in TVs, neon signs, and fluorescent lights.
1 minute.
1 minute. Okay, I will skip this. I will also skip this. This is how the plasma uses a transformer, which is 220 to 9,000 volts AC, or another one 220 into 225 volts DC. And these are the signals from the plasma. They also affect the power line channel. Here is still under the limits of the Senelic band. This is the fluorescent tube. I just want to show you the results. It's also under the limits. On narrowband, on broadband, they go wild. This is the metal halide lamp. The metal halide is not friendly on both sides. Okay, here when we use magnetic ballast, here when we use electronic ballast. As we see, the electronic ballast here is better than the magnetic. This one is mercury vapor lamp, which is a bit okay here, but here is not. This one is when using the electromagnetic, it exceeds the limits, which is dangerous for the PLC channel. This is the high pressure sodium. It exceeds the maximum allowed signal level when using electronic or electromagnetic ballasts. And we conclude that 7 types of LED lights were used or were tested for noise generation in the power line channel, and they produce interference in the narrowband channel, but this poses low risk or no risk sometimes to the PLC channel. And they also produce interference in the high band, which sometimes compete with or exceed the EMC levels. And LED lamps can be considered the most friendly, and mercury vapor lamps are the noisiest. And this is because mercury vapor lamps are the only ones that produce radiated signal as well, not just conducted signal. Thank you.
Okay, some questions?
I have a question. If you look at your curves for the LED lamps, right?
For LEDs, yes.
So they go from broad to narrow if you use more lamp.
Yeah.
Why is that?
Let's see the LEDs. These are the LEDs.
No, back. That one.
This one.
No, why is the
Okay.
why is
Here,
that?
because first of all, because this one is low wattage, so the more watts we use, probably the more harmonics we get. As you see, this is a 4-watt LED. It produces a lot of noise. This is one condition or one reason. The second reason is that we count a lot of the type of LED that we measure. Like as I always said, Philips is the best on LEDs. Of course, huh? Because you are from the Netherlands. Philips is the best always, and or not always, but we tested them many times, and we saw that Philips was the best company to produce LED lights. And also we take in consideration the output wattage.
I don't understand. If you put 3 times 1 watt, right?
Yeah.
So you have a peak distribution, say.
Yeah.
But if you take 1 LED lamp, it's much broader. Why is it in 3 LED lamps is it smaller than in the 1 lamp?
Okay, this one is one lamp that has 3 LEDs inside.
Yeah, okay.
They are together. So this is only one lamp. But I think the manufacturer here is different from
OFDM in different environments. The speaker is Tony. Okay, thank you.
Good afternoon, everyone. My name is Martin Soller, and I'll be presenting. I'll be presenting my work on creating a simulation for OFDM using MATLAB, and this project was supervised by Professor from Iceland. So it's a brief overview of what I'll be speaking about. So I'll introduce the wireless channel and how OFDM is relevant in the wireless environment. Just keep in mind that the simulation is not limited to the wireless environment. Then I'll briefly introduce the problem and discuss my objective. I'll go over the design process. I'll present some of the preliminary results I got, and then the future work for this project. So basically the thing with wireless communications is we keep on seeing an increasing demand for wireless communications. During the year 2014, we saw a 11% year-on-year increase in the mobile internet usage. This is due to the amount of mobile devices with access to the mobile internet. These devices require high bandwidth for applications such as voice, audio, and video. And we need a spectral, efficient, and robust solution. As you can see here, this frequency allocations for the United States, and one of the presenters this morning mentioned that this is swamped, and indeed it is. If you look here, there's a small white space where there's actually nothing allocated. So one of the methods is to actually expand beyond this spectrum and use higher frequencies. Another method is to design methods which is more spectral efficient. The OFDM is one such method. So OFDM is a kind of a multi-carrier multiplexing method, and it's an improvement over other multi-carrier methods such as frequency division multiplexing, whereas there's no gaps between multiple carriers. So the way OFDM works is the peak of one carrier coincides with a position where all the other carriers are zero. This allows us to easily extract each carrier at the receiver side. And we get to compact twice the amount of data in the same bandwidth as a traditional frequency division multiplexing method. So the total bandwidth used by the system is just the number of sub-carriers multiplied by the frequency spacing between the sub-carriers. So OFDM is actually used quite a lot in practice today in multiple digital audio and video broadcasting schemes, in wireless LAN standards, there's a lot of them. Also WiMAX, new LTE makes use of that, and then also in non-wireless environments such as Telecommunications, there's also various amount of standards for those. So now if we get into the problem statement, for this I'm going to discuss it in terms of a wireless environment, but it's still applicable to wired environments, so just to a large extent in most cases. So one of the problems we experience in a wireless environment is the effect of multi-top propagation. So consider that the scenario here where we have a transmitter and the receiver here, which can be mobile or static. So what will happen is the transmitter will transmit our signal in all directions. So there's various physical phenomena in this channel. So we'll have some deflection, diffraction, scattering, and so forth. So what this causes is we send a single signal, which will then propagate via multiple unique paths towards the receiver. Each of these paths might have a different amplitude, a different frequency, and a different phase, and it might also arrive at a different time interval at the receiver. More problems in the wireless channel is interference and fading. We have intercarrier interference. This is caused when there's a losing of optionality between two subcarriers. Then there's also intersymbol interference. This is caused when two distinct paths arrive within the same short time period at the receiver. Then we also have a loss in signal strength caused by large and small scale fading. Large fading is path loss, where we have an increasing distance between the sender and receiver. And then we also have shadowing. Small scale fading includes fading due to multiple effects, and then also time variance. Another important factor for OFDM is the idea behind the cyclic prefix. So this is used in order to reduce the effect of intercarrier interference. The idea behind this is we'll take the last data of a symbol, we'll copy it and place it at the front. So what this will do is, if two symbols arrive in a small period at the receiver, we can simply ignore this first part and still be able to retrieve the whole of the symbol. Okay. So for the project objective, I was tasked with creating a simulation for OFDM. So what is entailed is creating a simulation that will be able to apply any type of modulation. We can specify the cyclic prefix length and also the number of subcarriers. Then I will investigate how the system performs under various input parameters. And then for future work, I plan on designing a system which is optimized given a certain set of input parameters. So this is the system model which you might have seen from yesterday. So what will happen is we have a transmitter, a channel, and a receiver. So the idea behind the system is it will be extremely modular. So for this case, it's a wireless environment. But because I want to make the system to be modular in a sense, you'll be able to change this for the model that you present, the PLC channel or any other channel which will be relevant. So these are just some preliminary results I got. So this is for the performance of selected modulation schemes. So as you can see, as I increase the amount of modulation symbols, I actually experience a decrease in system performance. And this is described by the second equation here, where we can see if we increase the number of modulation symbols, which is indicated by n, will actually increase the probability of receiving a bit error. And also this is just for the varying of cyclic prefix length. So as we can see, we only get a benefit or increased benefit for cyclic prefix up till a certain limit, and then we actually start degrading the system performance. Then for my future work, I plan to derive some formula or some method of optimizing the OFDM system given the parameters. Then I also want to model various different environments such as the PLC channel and maybe VLC or any other relevant channel. And then I want to include some edit correcting techniques and codes. Yeah, just to summarize quickly what I said, I mentioned how the demand for mobile internet and the increase in access to the mobile internet motivates the investigation for more efficient and reliable methods. And I spoke about multi-path propagation, interference and fading. And then I quickly discussed my simulation results. And my final objective is to optimize the system. Thank you.
Okay, some questions? So maybe I give the first question. So although I'm not very familiar with this field, but for OFDM, we need some simulations in different environments. So recently for 5G, they consider something, for example, sparse coding process, SAMA, combined together with OFDM. Do you have some simulation or some consideration on it?
So at the moment, I have the simulation going that's according to the system model. But the idea is that these blocks are modular, so if we can find a new model that describes your system, then we can just replace one of them to work with that.
Another problem is that, so you talk about something about the prefix cyclic length. So I think that for the detection of the prefix cyclic length, it's not so easy. You have some method to
So usually how it works with mine is the receiver will be synchronized, so we'll know the amount, the length of the cyclic prefix. So I will know that it's set at 25%. That's what's commonly used. So I don't have to detect it, I can just 25% from the receiver.
25% for what? I mean for the detection of the location of the prefix.
Yes, that becomes another
Okay, so I think there's some, you should have some method to consider how about the distance, some kind of distance of your application and the real position. So which kind of distance can be used?
So at the moment how it works is I just take a percentage of the symbol, because how it's of the first time I read the symbol will arrive. So I know where the symbol starts.
Okay. So do you also do something consider how to use the prefix cyclic? How to use it?
And to define it.
Okay, suggestion.
Okay.
Okay, so more questions? So no more questions. So thank you very much. A moment. I remember that tomorrow morning we will have a travel, right?
That's in that processor, GPD. And then we have the radio frequency from head, which includes all these components. So all these components, my goal is to define all these physical functions in software. So we have analog to digital and digital to analog converters. first for the frequency. And we have, this is very important, we have logic cells, so 440,000 logic cells, and DSP blocks. So this is the second component. The second component is the radio board, the total board. So we have three stages. Sorry. So the first one is about the clock, how I generate the clock. So the clock generator is just there. Then we have the clock distribution for all stage, and then we have syncretism. So the first one is the transmission channels. So there is a ADC, digital to analog converter. This is a 16-bit DAC. Then we have an I3 modulator. I will explain that just after that. So working at this frequency. Then we have the gain, so 20 dB fixed gain. So this is the transmission channel, and then we have the reception channel, which includes demodulator, VGA, and ADC. Okay, about our research methodology. So first of all, I'm working about model and application of the SDR. So for the model, I just use MATLAB, so Simulink, to simulate my project. Then I have been working on the Z-board system on chip. So this includes the FPGA, the processor on Linux, and the I/O. Now what I will explain is this. So this is ADC peripheral. This is ADC-DC lighting modulator, and this is the scope. So this scope is just there. So this is a very simple scope embedded in Linux software, which allow you to show all modulation schemes and all data that you have to transmit. So the first step of my project was to download this IP. So this IP is available on Analog Device website. So you just have to download FMCOMS1 IP. Then you have a library in the project name. And what I have to do is to execute and program each block in VHDL and Verilog language. So what I have done is just here. Then I have the bitstream. So this is a benchmark diagram. So I have tested on Simulink, so device and test. So I have just made the model on Simulink of the software-defined radio. Then I have sources, so from the Vivado software, which is Vivado is a software, embedded software from Xilinx. So when this is done, I have my IP catalog. I can send the bit stream into another software, which is going to analyze the bit stream and the modulation. So this software is called Software Development Kit, and then I have my final application. Okay, so this is just to explain to you how the I3 modulator is working. So for me, I have two signals, one in-phase signal and one quadrature signal. So I can just send it into the FMCOMS1 component. So the first signal and the second one are 90 degrees out of phase, and the message is also 90 degrees out of phase. So there is the original one and the 90 phase shifted version. So now what the result, this is the progress. Sorry. So I have analyzed the bit stream using Vivado software. So I have VHDL and Verilog files on the FPGA. I have done the digital add conversion, and I have done a BPSK modulation using two things. Sorry. So the first one is GNU radio, which allows you to make a very simple modulation. So for that, I just need one transmission and one reception USRP, which is there. And the next step will be to do the 16-point modulation and try to compare this one with the BPSK modulation. So the next step will be the digital down conversion, the filtering, and the fast Fourier transform. Okay, so as a conclusion, I will just make a small think about advantages of this board, this FPGA, and disadvantages of this FPGA for software-defined radio. So the most important thing about FPGA is the reconfigurability. So this is very powerful for software-defined radio. It means that if you want to change one frequency at each step of your project, you can do that using FPGA. So the second thing about advantages is the reduced component cost. maturity. This Z board, this FPGA, includes AES and SHA function algorithm, but it's very hard to program that in VHDL. So you have to first compile or to use another language, that's Verilog and VHDL to do that. So this is that on this FPGA. And the last disadvantage is the overall cost. So the board I'm working on is about $1,300. So for the full system on chip, which is, I think, bad for doing software-defined radio for this project. So this is just useful links. Sorry. These are just useful links you can use for doing FPGA on side Z-board. So you can just go to Z-board website, analog device website, and follow that tutorial, that wiki. And this is just some references, very useful to work on FPGA as well. Thanks for your attention.
So some questions for this topic?
Okay. Okay. So is the IQ modulation, is it on the board or did you have to program it yourself?
Yeah, it's on the board. It's on the daughter board. I can show you. It's there. So this is the modulator, and I can just take my inputs, so my in-phase signal and my quality signal into that modulator at these frequencies.
What did you tell them later about IQ modulation?
Sorry?
So you had another slide about IQ modulation.
Yeah.
What was that?
You mean another?
You explained what the
Five
modulator.
slides later.
IQ modulator, you explained later.
Oh. So this is a modulator working at this bandwidth, 406,000 megahertz.
Maybe this is another.
You can just speak louder.
That's not it. No, I don't think.
So this is just the modulator. And to do an IQ modulator, I just need to have two signals, one for input, so in phase and quality signal, and I can just put it in Vivado software into that module. So asking for that module, ADL 537.
Okay. I thought, so you do it yourself or you can do it?
I'm doing that by myself.
Yourself. So did you also develop a user programming system
Instead?
for your software, the software
Yeah.
radio, right? You also develop a user programming system or no?
No. What I can do is to program this, to program all the daughter board. So this board for radio communication. Then what I have to do is to program the FPGA in C.
Okay. I think it's a lot of work. It's good work. Because already some software, USRP and some
Yeah,
kind
but
of
USRP
algorithm
was just
something.
was just an example to do the modulation, the PSK modulation.
So you only have one version. Do you have a Windows version or something?
This was done on a Windows machine.
Oh,
But if you want to use the final software-defined radio, you have to get it from the Linux machine.
okay. More questions?
Did you look at efficiency of programming FPGA?
Yeah. The efficiency.
Yeah.
You mean the
Comparison with some other software.
oh
No, I mean
you mean the
Okay, ladies and gentlemen, this is a talk which is not about information theory. This is about this is about PLC and some real hardware problems, and it's about communication theory. Now, I'm talking about fundamental aspects of common mode conversion in C-mode PLC networks. And the first question we seem to have is just see if I've got a...
German is okay.
Power line.
so the first question that you should ask me is, what is common mode current? Now, common mode current is something that I'm very interested in. I'm not an information theorist. I'm actually an electromagnetics guy. And common mode current occurs when there is current flowing in a circuit that is outside the circuit. So you'll see there's differential mode current flowing, which is the normal type of currents that we all know. That's what's on a circuit diagram. And then there is common mode current, which flows from the load through the ground back to the load again. And that IS and IR is just the incoming, the signal, and the returning currents. So why are we interested in common mode current in PLC, in power line communications? Well, the first thing I'll show you, and that's what this talk is about, is that the signal levels available on the common mode channels in MIMO and in CMO, single input, multiple output networks, and multiple input, multiple output systems or channels. The signal levels is determined by the common mode. So you'll see, I'm going to show you some practical results to show how that works. Then, something that's close to my heart is the electromagnetic compatibility of the PLC network and the emissions of a PLC network. If we start emitting all over us the power lines, that happens in common mode and with common mode current. And we are also on a program. I did a paper last year at ISPLC, and I showed that you can actually communicate wirelessly or contactlessly with the power line network by using an antenna. And that is also determined by the common mode or the antenna current. Now, this is the little graph that you usually see in the information network books. And what happens is that there's a CMO, single input multiple output PLC system or a channel, and it's between the live and the neutral of the power lines, and then there's always a little cloud. And information theorists like this little cloud. And then in this cloud, something happens, and something magical happens. And what happens is that the differential mode, the normal signals that you have on your live and your neutral, actually starts coupling to another plane or another dimension, not a dimension, but another plane, which is the common mode plane. And what we are interested in getting is we are interested in getting information over this PLC network. And the information, what we're interested in is the transfer function of that input voltage to the output voltage there, that input voltage to the output voltage there, and that input to the output over there. And that's what we're interested in. So I'm going to show you why MIMO actually works. It was an eye-opener when we saw it practically for the first time. Now, the experimental setup that we used was a piece of wire, just 3 wires. And there's 3 wires. There's a live and a neutral wire that come down, and we've got a 50 ohm load here, 50 ohms down to an earth wire. And the interesting thing that we did was we didn't connect the earth wire at all. The earth wire was floating in the air. And what did we see if we started measuring the transfer function of this channel? Well, we saw this, that in the differential mode, we get a -2 dB drop in the channel, which is normal losses, and it's within the measurement range of our equipment. And in the common mode, nothing particularly interesting happens, except that it's very low. And then suddenly something funny happens around that's 10 megahertz, 20, 30 megahertz for this 2-meter piece of wire. And that interesting thing that happens is that you are transgressing from the so-called lumped element model or lumped element behavior of a PLC network to a so-called transmission line model, or the transmission line behavior. So we thought, okay, that's interesting, but we are still getting information out on the differential mode as per what you will usually understand or expect. So we did something funny. We used absolutely the same circuit, but instead we made a discontinuity in the balance, electromagnetic or 3D balance of this circuit. And we added a leg. So from a circuit point of view, this circuit and this circuit is the same thing. But from a MIMO point of view, this is what you get out. So what happens here is that in the beginning, yes, we've got the lumped circuit behavior, and then suddenly at a couple of megahertz, we start seeing transmission line behavior. Now the differential mode, which is the normal mode that you would usually tap off for the signal, is this green one. And you'll see here there's a little null in the green one, and then there's a big null at the end over here. And that is where MIMO actually works. Because what MIMO does is you put a signal into differential mode, but you tap that signal, you tap in one of the common modes. So the channel falls away at this frequency, the normal differential mode channel falls away, and it falls away there, but in the common mode, you actually get a channel again. So to make it much more interesting and to see how we want to find out how real-life PLC networks behave, we opened the circuit, and I'm talking about, sorry, I had to introduce him in the beginning. I'm talking about my colleague, Mr. Ashraf Sheri, and he helped me with all these measurements. He's doing his PhD in this field at the moment. And what we did was we opened that node over there as if it's a switch, a light switch that you switch on, or a plug that you switch on or off. And what we got is another transfer function. This time, if you look at the lump circuit behavior at the lower frequencies, you can see that there's a lot of loss of signal, which is understandable because at low frequencies, close to DC, close to 50 hertz, close to a couple of kilohertz, the switch actually opens the circuit, and there should be a loss of signal. But the interesting thing is that from a fairly high frequency, which is 10 megahertz in this case, we started getting coupling, and we started getting a channel even though the switch has been switched off. So what happens is that there is coupling, even though that is open, there is coupling between this neutral line and this earth line, and you can pick it up on the MIMO channels at the end. So again, what we are trying to do is to understand how common mode actually produce, or how common mode is produced or coupled from differential mode. And there is two ways in describing common mode in PLC. The one is the lump circuit theory, and what you do, there's a limit. I've heard the word bound. I don't know if it's a bound, but there's a region, and the region is lambda over 20 or lambda over 10, depending on who you talk to, where lambda is the wavelength of the frequency that you're working with. Now, and this is a so-called electrically long system, where the lump circuit theory dominates what happens. If you're looking at systems where lambda is larger, the length of the PLC line is larger than lambda over 20, we start using multi-conductor transmission line theory to explain how common mode actually works. So I'm not going to bore you today with this, but this is one of the things that we are looking into and trying to understand, and it's called the imbalance difference model. Now, the imbalance difference model was first proposed by a Japanese gentleman with the name of Watanabe, and they looked at common mode generation on PC boards. And it is a lumped element generation of models that actually tells you how common mode gets generated in a circuit, and then he has all sort of things to say about what that common mode current does, and you can have equivalent circuits for the common mode current. And for me, it took me a couple of months and years to really understand this, but after a while I got used to this, and from a lump circuit approach, I can tell you today where common mode comes from. Now, the long and the short story is common mode comes from unbalance in a system. Okay?